So if you remember, we had 3 questions that we were going to investigate to get a better understanding of what this sampling distribution of sample means are. So the first question, we talked about the law of large numbers and why we're allowed to use the sample mean x bar to replace the population mean mu. The second question, we looked into that standard deviation and why we're dividing by that square root of n. So our third question is, why or when are we going to get a normal distribution for our sampling distribution? So far, all of our original population distributions were normal. And when that happens, it means your sampling distribution will also be normal no matter what sample size you use. But what happens if your population distribution is not normal? So there are a couple different ways of tackling this, but let's look at a simulation. So with this simulation, we're asking the question, what happens if we estimate the population mean mu using the sample mean x bar by taking lots and lots of samples of a specific size from the population and finding each mean? So the process behind that would be taking a sample, calculating the mean, and repeat that over and over and over again, and then plot those values in a histogram and analyze the shape. Doing that by hand is incredibly time consuming, so we're going to use a simulation to help us with this. You'll see the link at the bottom of the PowerPoint slide, and then there's also a link on Canvas to help you find that. So I'm going to join you over in that app, and we'll take a look at kind of investigating through simulation what happens with a not normal distribution. All right, so here's where that link leads to for the simulation. And you can choose this button that says begin in kind of the upper left corner. And so it gives us a population distribution at the top. This one is normal. And the spot right below it, there's nothing in there yet. But if I click this button that says animated, it'll pull a sample of size 5, find the average, and then drop a block that represents that average to the third graph below. So that third spot is where we're going to start building our sampling distribution. So I can pull another sample, it'll find a new average and drop a block. I'll repeat that again. Okay, and so now I am up to a sample size of 5. And you can see that actually right over here to the left of the sample distribution. I'll tell you how many reps or how many samples you're on. So I could do this one at a time, but fortunately the person who created this made it a little bit faster for us. If I click this 5, that'll take me up to 10 samples and 10 averages, 15, and then 20. So if you look at the notes, the first place it says to stop is when you get to sample size or 20 averages here. So when I look at this does appear to be fairly normally distributed. So the question says, when the sample size gets to around 20, what shape does this look like it has? So I'm going to say normal, at least somewhat here. Next, we want to go up to a sample size of 50. So I'm going to add these 5 at a time till I get to 50. Okay, so maybe a tiny bit left skewed, but this one's also looking pretty normal. And then let's go all the way up to a sample size of 100. Okay, so starting to look a lot more normal. And I can actually add these much faster. So we can add these at a rate of 10,000 or 100,000 samples pulled, and then averages calculated. And you can see in the long run, this is going to be very normally distributed. Okay, but we already knew this. We already knew that a normal population distribution is going to give us a normal sampling distribution. What happens if it's not normal? So up at the top where this parent population is at, you can click the checkbox and you can choose uniform or skewed. And so there's a spot in the notes for you to choose those two and go through and pull 20 samples, 50 samples, and 100 samples and evaluate those. So I'd love for you to go ahead and choose that uniform and try these problems out on your own, play around with this simulation a little bit and get a good feel for what happens. All right, so I'm going to start pulling samples of 5 so I can get to 20 in a reasonable amount of time here. So if I pull 20 samples out of this and find their averages and plot them, I have this thing that I'm not really sure what it looks like. It's definitely, if it's normal, it's pretty flattened out. So not the most normal looking thing, but let's keep adding these. So now we're at 50. And I see lots of bumps and wiggles in there, but sort of closer to unimodal. And we'll get us up to about 100. So still kind of some problems. And then, okay, so I added 10,000 and here we go. We're starting to see this coming up to being much more normal. So in the long run here, if you have that uniform distribution, you will eventually get to something that looks normal. We're going to talk about when that is in just a little bit. Let's do the same thing with the skewed one. So we can pull these samples of 5 at a time. And as we would expect, these are going to be more toward the left side because that's where the greatest set of values are at. And so as I add these along, so here's 50. So we're starting to get actually fairly normal looking. So we're a little over 100. So normal with a little bit of right skewed. And now as I start adding them at a rate of 10,000 or 100,000, I can really start to see that normal distribution come out. Okay, so let's go back to the PowerPoint and take a look at when we're going to get this to happen. Okay, so we saw in the simulation that the more samples we're pulling, no matter what that distribution is, we are going to get somewhere close to something that looks pretty normal looking. So the central limit theorem is what's going to guide us for how we decide when we get to claim that our sampling distribution is normal. So it says, draw a simple random sample of size n from any population. The central limit theorem says that when n is large enough, the sampling distribution of the sample mean x bar is approximately normal. So we actually have an example of a normal distribution, a skewed distribution, and a uniform one. And they show you what it would look like if you're using a sample size of 2, a sample size of 10 each time, or a sample size of 30. So in this simulation, we were using a sample size of 5. And so it took a while for things to kind of shake out into the normal distribution. So what turns out happening with the central limit theorem is that the word large actually means a sample size of 30, if you can believe that. So if you're pulling samples that are size 30 or greater, and you pull them over and over and over again, and you plot them, you are guaranteed from the central limit theorem that you are going to have that normally distributed sampling distribution. So if your original population is normal, then you can go ahead and use any sampling size and get yourself to that sampling distribution. If your original population is not normal, then you want to check to make sure you have a sample size of at least 30. And if you do, then you can also use this normally distributed sampling distribution. So central limit theorem applies to sampling distributions, not to the distribution of the sample itself. So when we plot the average for each of those samples, that's where our CLT is going to kick in here. So one of two things, either the original has to be normal or your sample size has to be 30 or greater.